The El Niño Southern Oscillation is undeniably the largest and most consequential natural disruption to the Earth's climate system. A standard El Niño occurs when sea surface temperatures in the equatorial Pacific rise 0.5 degrees Celsius above normal. A super El Niño is declared when the Oceanic Niño Index records an anomaly that reaches or exceeds plus 2.0 degrees Celsius. Crossing this threshold initiates an exponential escalation of global climate disruptions. While many view El Niño as a seasonal weather pattern, its oceanic shifts serve as a catalyst for severe stress throughout the marine food web. The impacts extend to the land, where shifted air masses spark massive forest fires in normally wet tropical regions. The final tier of this hazard is epidemiological, the potential for a sudden, explosive amplification of global disease outbreaks. A super El Niño represents a coupled chain reaction across planetary physics, ecology, and epidemiology. The baseline state of the Pacific is the Walker circulation. Strong trade winds blow east to west, pushing warm surface water toward Asia, which allows cold, deep water to upwell near South America, establishing the thermocline, the boundary between the warm surface and the frigid depths. El Niño begins when these trade winds weaken, removing the force that keeps the Pacific's thermal structure in balance. Without the wind holding it back, the massive pool of warm western water sloshes back toward the Americas, overriding the cold water upwelling zone. This creates a positive feedback loop. The eastward warming further weakens the winds until the thermocline completely flattens and seals the ocean's surface in heat. This physical displacement of warm water relocates vigorous tropical thunderstorm development thousands of miles to the east of its usual position. These misplaced thunderstorms punch into the atmosphere, disrupting the planetary Rossby waves that guide our global wind patterns. By flattening the ocean's thermal gradients, the super El Niño reorganizes the Earth's upper atmospheric architecture. This reorganization is devastating for the Humboldt Current off South America, one of the most productive marine regions on Earth. The eastward surge of warm water creates an impenetrable thermal cap, preventing nutrient-rich water from rising to the surface. Without these deep-water nutrients, the microscopic phytoplankton that form the base of the marine food web starve and vanish. This triggers a trophic collapse, as predators and zooplankton face starvation in sequential order. The impact is quantifiable in the Peruvian anchoveta fishery, which provides 20% of the world's fish meal. During super El Niños, anchoveta catches have plummeted by over 50%, causing global aquaculture costs to skyrocket. The warming also triggers a second global hazard: mass coral bleaching. Heat stress forces corals to expel their symbiotic algae, removing their primary energy source and effectively starving them. This warming event effectively asphyxiates the foundation of the marine food web, triggering systemic starvation. These impacts travel through teleconnections, cascading climate effects that strike regions on the opposite side of the world via the altered jet stream. Over the western Pacific, El Niño establishes stubborn, suffocating high-pressure systems. For Indonesia and Australia, this results in complete monsoon failures and prolonged droughts. These droughts desiccate tropical rainforests and peatlands, lowering ignition thresholds and sparking massive, uncontrollable fires. Conversely, the jet stream carries vast low-pressure zones to the Americas, dumping torrential rainfall. The result is catastrophic flooding, completely shattered infrastructure, and deadly, fast-moving landslides from California all the way to Peru. This data shows how these dry and wet anomalies lock into place across specific geographic zones during an event. Teleconnections weaponize the atmosphere, transforming an equatorial thermal anomaly into a global matrix of extreme weather. These meteorological extremes act as multipliers for a hidden danger: the epidemiological amplification of deadly pathogens. By modifying local temperature and moisture, El Niño expands the habitats and accelerates the life cycles of disease vectors. In flooded regions like East Africa, inundated sanitation networks contaminate drinking water with sewage, triggering explosive cholera outbreaks. Warmer temperatures also allow malaria-carrying Anopheles mosquitoes to survive in highland areas that were previously too cold for the disease to transmit. Heavy rainfall causes dormant, infected mosquito eggs to hatch en masse, driving major, widespread Rift Valley fever epidemics. In the U.S. Southwest, extreme precipitation creates food abundances that drive massive rodent population surges. These surges lead to significant, predictable spikes in bubonic plague and hantavirus transmission to humans. In teleconnected regions, the intensity of these outbreaks is statistically proven to rise by up to 28% during an El Niño. The ultimate human cost is measured in epidemiology, as fractured climates engineer environments for disease proliferation. The Super El Niño pushes the Earth's climate system to its breaking point, exposing the fragility of our human infrastructure. Greenhouse warming complicates this cycle, as the eastern equatorial Pacific is warming faster than the surrounding regions. This reduces the east-west temperature differential, keeping baseline conditions perpetually primed for extreme warming events. Climatologists project that this new baseline could double the frequency of extreme super El Niños in the coming decades. Our defense relies on anticipatory action, using oceanographic data to cut fishery quotas and pre-position vaccines months before the thermal threshold is breached. The Super El Niño has become a meticulously mapped systemic hazard that demands an equally systemic defense.